requirement, one has to decide whether liquid suction heat exchanger is required or not. Okay. And one thing I would like to point out here is that the results or the trends may not be same for all the refrigerants. It may vary from refrigerant to refrigerant. Okay. For some of the refrigerants, liquid suction heat exchanger is found to be beneficial. For example, for systems like R12, liquid suction heat exchanger is good. Okay. But for R22, it offers certain advantages and certain disadvantages. Okay. So, ultimately a trade off is required between the benefits and the disadvantages. Okay. Now, let me discuss the second problem. This is a problem on vapor absorption refrigerant system. So, let me read the problem. A vapor absorption refrigeration system based on water lithium bromide has a refrigeration capacity of 300 kilowatts. The system operates at an evaporator temperature of 5 degrees centigrade and a condensing temperature of 50 degrees centigrade. The exit temperatures of absorber and generator are 40 degrees and 110 degrees centigrade respectively. The concentration of solution at the exit of absorber and generator are 0.578 and 0.66 respectively. And it is also mentioned that we can assume the effectiveness of the solution heat exchanger to be 100%, exit condition of refrigerant at evaporator and condenser to be saturated. That means you have saturated vapor at the exit of evaporator and saturated liquid at the exit of condenser. Okay. The third assumption is that the condition of the solution at the exit of absorber and generator are at equilibrium. Okay. That means absorber exit and generator exit, you have equilibrium solutions. And enthalpy of solution at the inlet to the absorber may be obtained from the equilibrium solution data. Okay. That means for obtaining the enthalpies of these 3 points, that is at the exit of absorber and generator and also at the inlet to the absorber, can be obtained from the equilibrium HTX data, that is what it means. And the enthalpy of superheated water vapor can be obtained from this equation HV is equal to 2501 plus 1.88 T, where HV is in kilojoule per kg and T is in degree centigrade. Okay. So, this is the information given, and from this information we have to find out the mass flow rates of refrigerant, weak and strong solutions, heat transfer rates at the absorber, evaporator, condenser, generator and solution heat exchanger, COP and second law efficiency, and finally solution pump work. And for obtaining the solution pump work, we can take the density of solution to be constant at a value of 1200 kg per meter cube. Okay. Okay, let me summarize the information given. Refrigeration capacity is given to be 300 kilowatts, evaporator temperature 5 degree centigrade, condenser temperature 50 degree centigrade, absorber temperature 40 degree centigrade, generator temperature 110 degree centigrade, weak solution concentration zeta Ws is 0.578 and strong solution concentration zeta Ss is 0.66. Effectiveness of solution heat exchanger is 1 and density of solution is 1200 kg per meter cube. So, this is the information given. So, now let me once again I have already explained this while discussing vapor absorption refrigerant systems, but let me once again quickly explain the system and show the various state points. Okay. So, as you know, we have the evaporator here, this is the evaporator, this is the absorber, this is the generator and this is the condenser. In addition, you have the expansion device for the refrigerant and you have the expansion device for the solution, you have the pump for solution and this is solution heat exchanger. Okay. And as you know, the working this thing low temperature low pressure vapor at 0.4 enters into the absorber, it comes in contact with strong solution coming from the generator at 0.10. So, the solution absorbs this vapor and heat of absorption is taken out QA and the resulting weak solution is pumped in this pump to the high pressure and the high pressure weak solution flows through the solution heat exchanger where it is preheated by taking heat from the hot solution coming from the generator and this preheated solution which is weak, that means which is strong in refrigerant, goes to the generator where heat is supplied to the solution. As a result of this heat supply, refrigerant is separated from the solution. So, refrigerant at high pressure and high temperature goes to the condenser. In the condenser it condenses and the heat of condensation is rejected to a cooling water or a heat sink, and the condensed refrigerant liquid at high pressure is throttled in the expansion device to low pressure, and because of this the pressure and temperature drops. So, this low pressure low temperature refrigerant is sprayed into the evaporator where it evaporates, taking heat from the external heat source. So, you get the useful refrigeration effect QE, okay, and the cycle continues, the vapor goes to the absorber and the cycle continues, and the solution which is now stronger in absorbent and weaker in refrigerant at 0.8 flows through the solution heat exchanger, then the expansion device, and is then sprayed into the absorber so that it can again absorb the refrigerant vapor. Okay. So, again look at the points. Point 1 is the exit of the generator, it is pure refrigerant vapor at high pressure and high temperature at the exit of the generator. Point 2, okay, point 2 is the refrigerant liquid at high pressure, saturated refrigerant liquid at high pressure, and it is at the exit of the condenser. Point 3 is a low pressure refrigerant at evaporator pressure, and point 4 is low temperature low pressure saturated vapor. Point 5 is weak solution at evaporator pressure. Point 6 weak solution at generator pressure. Point 7 preheated weak solution at generator pressure. Point 8 strong solution at generator pressure and generator temperature. Point 9 is strong solution, so now cooled strong solution still at high pressure. Point 10 is the strong solution at evaporator pressure. Okay. So, now we will find out the properties of all these points, because if we want to find out the performance we need to know the properties. Okay. So, for finding the properties we make the assumptions that the refrigerant vapor at generator exit to be in equilibrium with solution leaving generator. Okay. This assumption is required to find the enthalpy of the refrigerant vapor. Okay. That means it is given that the solution leaving the generator is at 110 degree centigrade. Since the vapor is at equilibrium with this, vapor also has a temperature of 110 degree centigrade. So, once you know this, you can find out the enthalpy of the vapor, because it is given that enthalpy of the vapor can be obtained from the expression 2501 plus 1.88 into T, where T is 110 degree centigrade. So, from that expression you find that the enthalpy of vapor at generator exit is 2708 kilojoule per kg. Okay. Then from the effectiveness of solution heat exchanger, again effectiveness, as you know, is defined as the MCP minimum into delta T actual divided by MCP minimum into delta T maximum. In this case the mass flow rate of the strong solution is less than the mass flow rate of the weak solution, and if you assume that the Cp values are almost same, then you find that it is the strong solution which has the lower MCP product. As a result, the effectiveness of heat exchanger is defined in terms of the strong solution flow rates and strong solution specific heat. Okay. So, you can write effectiveness as MSS into CPSS into delta T actual, which is T8 minus T9, divided by MCP of strong solution into delta T maximum, which is equal to T8 minus T6. And it is given that this value is equal to 1, because this heat exchanger is 100% effective. So, from this you can easily show that T9 is equal to T6 is equal to 40 degree centigrade, because T8 and T8 it is very easy. T6 is given to be 40 degree centigrade. Now, you can use the property charts and find the properties. Okay. Remember that I have discussed PTX and HTX chart. So, to find this property we will be using PTX and HTX charts in addition to the refrigerant properties. Okay. Let me quickly go through how properties have been evaluated. Point 1 is at the exit of the generator, and this is pure refrigerant vapor. At this point we know the pressure, okay, because this pressure is nothing but the saturation pressure corresponding to the condensing temperature, okay, which is equal to 50 degrees. So, this pressure is known to us and temperature is known to us. So, from this we have found the enthalpy. Okay. and point 2 is the exit of the condenser, as I have already discussed. It is saturated liquid. So, we know the temperature to be 50 degree centigrade and the pressure is saturated pressure at 50 degrees, which is equal to 123.3 millibar. So, from this equation you find the enthalpy is equal to 209 kilojoule per kg. Point 3 is the exit of the expansion device. So, the temperature is same as the evaporator temperature, pressure is equal to evaporator pressure and the enthalpy is same as the inlet enthalpy, which is equal to 209. Okay. So, we know the enthalpy, and point 4 is nothing but the exit of the evaporator. So, we know the temperature 5 degrees and pressure is 8.72, and we know that at this condition it is dry saturated. Okay. That means quality is 1. So, from this information find out the enthalpy of saturated vapor at 5 degree centigrade, which is 2510 kilojoule per kg. Point 5 is now solution. Okay. This is the weak solution leaving the absorber, and what do we know at this condition? We know that the temperature is 40 degree centigrade and the pressure is same as the evaporator pressure, that is 8.72, and it is also mentioned that the concentration is 0.578. Okay. So, this is given as the input, concentration is given as the input, temperature is given as the input. So, using the concentration and temperature and concentration data, you can find out the enthalpy values from equilibrium HTX chart. Okay. Now, point 6 is nothing but the exit of the solution pump, and if you assume that the solution pump work is negligible, then you find that the enthalpy remains same as the inlet enthalpy. Okay. That is the reason why we have taken enthalpy as minus 154, and the pressure will be obviously the condensing pressure, that is 123.3, and there is no mass transfer. So, concentration remains same, that is 0.578. And point 7 I will explain to you. Point 7 is nothing but the condition of the weak solution at the exit of the solution heat exchanger. All that we know about point 7 is that the pressure is 123.3 and we also know the mass fraction, which is equal to 0.578, but this information is not adequate to find the enthalpy. Okay. So, this enthalpy has to be obtained from energy balance. Okay. I will show you the energy balance equation. Then point 8 is the strong solution condition at the generator exit. So, at this point we know the temperature to be 110 degree centigrade and we also know the concentration to be 0.66. So, from the temperature and concentration data we find the enthalpy to be minus 13 kilojoule per kg, and pressure is of course same as condensing pressure, and point 9 is the exit of the solution heat exchanger, and from the solution heat exchanger effectiveness we find that this temperature is same as 0.6, that is 40 degree centigrade. So, we know the temperature and we also know the mass fraction. Okay. And if you assume that you can use the equilibrium HTX chart, from this and this you can find out the enthalpy, which is equal to minus 146. Okay. So, that is how we find the enthalpy, and point 10 finally is nothing but the exit of the solution expansion device, and if you are assuming this expansion process to be isenthalpic, enthalpy will remain same as minus 146, and we also know that the concentration is 0.66 because there is no mass transfer, and pressure is same as the evaporator pressure, that is 8.72. Okay. So, once you have all the points and once you have the PTX and HTX charts, then if you can locate the points carefully on the PTX and HTX chart, then you can find out all the required state point property data. Okay. Once you have all the property data, the problem becomes very simple, because all that you have to do is take each component and apply mass and energy balance across each components. So, in you might have noticed that one of the major tasks is to obtain the correct property values. Okay. If you do not get the correct property values, final answers will be wrong. Okay. So, for that reason you should know the cycle properly. Okay. And if you can plot the cycle on pH or TS and locate the point, then it becomes easier. Okay. So, once we have the properties, we can quickly find out the required mass flow rate of refrigerant. We apply energy balance across the evaporator. This is nothing but steady flow energy equation, and we assume kinetic and potential energy changes to be negligible. So, mass flow rate is simply equal to QE divided by H4 minus H3, which is equal to 0.1304 kg per second. Okay, because QE is given to be 300 kilowatts and H4 and H3 we have obtained. Then circulation ratio, because we have to find out the mass flow rates of strong and weak solutions. So, first let us find the circulation ratio. Circulation ratio, as you know, is defined as the ratio of strong solution flow rate divided by the refrigerant flow rate. Okay. And from mass balance across the absorber, we have seen that for water lithium bromide systems the circulation ratio is equal to concentration of the weak solution divided by the difference between the strong and weak solution concentrations, that is zeta Ws divided by zeta Ss minus zeta Ws. Okay. And zeta Ws from the input data is equal to 0.578 and zeta Ss is 0.66. So, if you are substituting these values, you find that the circulation ratio is 7.05. So, once you know the circulation ratio, you can easily find out the mass flow rate of strong solution, which is nothing but circulation ratio into mass flow rate of refrigerant, which is equal to 0.9193 kg per second. And mass flow rate of weak solution, this you can easily obtain from the mass balance across the absorber, and we have shown that this is nothing but circulation ratio plus 1 into mass flow rate of refrigerant. Okay. So, if you are substituting these values, you find that mass flow rate of weak solution is nothing but 1.05 kg per second. Obviously, the difference between the weak solution flow rate and the strong solution flow rate should be equal to refrigerant flow rate, okay, because the mass has got to be balanced. So, we have found the required properties. Now, I mean required mass flow rates. Now, let us find out the heat transfer rates at various components. Okay. Evaporator QE is equal to 300 kilowatts, this is the information given in the problem itself. Then let us come to the absorber, and from energy balance of the absorber, what is the, how do you write the energy balance of the absorber? So, this I have explained many times, you just take control volume across the absorber, energy coming in is energy going out, and we want to find out QA. Okay. So, if you are writing energy balance, you find that energy going out is nothing but QA plus mass flow rate of weak solution, that is at 0.5 into enthalpy at 0.5. Okay. This should be equal to energy coming in. So, energy is coming in by the way of mass flows. So, energy coming in is m into H1, this is nothing but the energy contained in the refrigerant plus m strong solution into H10. Okay. So, this is the energy balance for the absorber. So, from this equation we can find out QA, because we know all these mass flow rates and enthalpies. Okay. So, from energy balance QA is equal to mH4 plus MSS into H10 minus MWS into H5, and all the mass flow rates have been computed and all the enthalpy values are known to us. So, if you simply substitute these values, you find that the required heat rejection rate at absorber is equal to 354.74 kilowatt. Similarly, you apply the energy balance for the generator. For the generator, if you write the energy balance, again you can take okay. So, we take again the control volume across the generator. So, from this you can find that energy coming in is equal to energy going out. Energy going out is m into H1 plus M8, that is M strong solution into H8, right, and energy is also coming by the way of weak solution, this is MWS into H7. Okay. So, this is the energy balance across the generator. Similarly, let me explain energy balance across the condenser and all, so I need not come here again. So, from energy balance across the condenser you find that QC is equal to M into H1 minus H2, and energy balance across the expansion device is nothing but H2 is equal to H3, and across the evaporator we have already shown QE is equal to M into H4 minus H3. Okay. So, from this we find that energy balance is MH1 plus MSS into H8 minus MWS into H7. As if you remember, I said that H7 enthalpy at 0.7, that is the weak solution enthalpy after solution heat exchanger, has got to be obtained from energy balance across the solution heat exchanger. Okay. So, let me give that equation. So, enthalpy of weak solution at the exit of solution heat exchanger is obtained from the energy balance equation, and the energy balance equation for the solution heat exchanger is very easy. Energy gained by the weak solution is equal to energy lost by the strong solution, that is what is shown here. Energy gained by the weak solution is MWS into H7 minus H6, this is equal to energy lost by the strong solution, that is MSS into H8 minus H9. So, this gives H7 is equal to H6 plus MSS into H8 minus H9 divided by MWS, and we know everything on the right hand side. That means we know all the enthalpies, we also know the mass flow rates. So, if you substitute these values, you find that the enthalpy is minus 37.5 kilojoule per kg. Now, if you substitute this enthalpy value in the energy balance for the generator, you can find out what is the required heat input to the generator QZ. Okay. So, we find that QZ is 380.54 kilowatts. So, this is the energy that is to be supplied to the generator. Then condenser, as I have already explained, QC is equal to M into H1 minus H2.